Hello everyone, my name is Jagdish Atole and in continuation of series of lectures on theories of failure, in this session we will discuss the fifth failure theory, that is maximum shear strain energy theory. In the previous session we discussed about some failure theories like maximum principal stress theory or Rankine's theory, then maximum shear stress theory or Coulomb-Guess Tresca's theory, and maximum principal strain theory or Saint-Venant's theory. Then we discussed about the maximum strain energy theory or Hayes theory. If you haven't watched those videos, then you can watch that with the link provided in the description. Do subscribe, like, share and press the bell icon so that you never miss any new learning video from the Designgekz. Without any further delay, let's deep dive into the topic. The maximum shear strain energy theory is also known by the maximum distortion energy theory. It was initially developed by the Austrian scientist Richard von Mises, and the number of other scientists were also involved in refining it. So it is also known as von Mises, Huber and Henke's theory or Henke-von Mises theory. According to this theory, the failure or yielding occurs at a point in a member when the distortion strain energy, which is also called as the shear strain energy, per unit volume in a biaxial or triaxial system reaches the limiting distortion energy per unit volume as determined from the simple tension test. Mathematically, the condition of failure is UD greater than UD in simple tension test. The limiting distortion energy means the distortion energy at yield point. And what is meant by distortion? The distortion means the change in shape of an object. Suppose we have this cuboidal body and we apply the compressive force or compressive load on this body. Now because of this applied force, the body gets changed like this, either first, second or third. So the distortion energy theory discussed about this shape change. The earlier theory which we discussed in the last video, that is total strain energy theory, which discussed only about the volumetric strain. But this distortion energy theory discussed about volumetric strain and distortion both. This is the marginal difference between the total strain energy theory and distortion energy theory. Let's understand this distortion energy theory with some mathematical equation. Suppose we have this cuboidal body like this and it is subjected to triaxial loading as sigma 1, sigma 2 and sigma 3. Since the body is subjected to triaxial loading, there will be the strain in three dimensions which is induced by these stresses as epsilon 1, epsilon 2 and epsilon 3. Now, when the component is subjected to such loading, we can write the equation for total strain energy as U is equal to 1 by 2 sigma 1 epsilon 1 plus 1 by 2 sigma 2 epsilon 2 plus 1 by 2 sigma 3 epsilon 3 as discussed in the total strain energy theory. Let's consider this as equation 1. And we know as per the generalized Hooke's law, epsilon 1 is equal to sigma 1 divided by E minus mu sigma 2 divided by E minus mu sigma 3 divided by E, which can be simplified by taking 1 by E as common, which gives epsilon 1 is equal to 1 by E into sigma 1 minus mu times sigma 2 plus sigma 3. Similarly, for epsilon 2 and epsilon 3, we can write as epsilon 2 is equal to 1 by E into sigma 2 minus mu times sigma 3 plus sigma 1, and epsilon 3 is equal to 1 by E into sigma 3 minus mu times sigma 1 plus sigma 2. If we substitute the values of epsilon 1, epsilon 2 and epsilon 3 in the equation 1 and simplifying it, we will get U is equal to 1 by 2E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. So this is the total strain energy in three-dimensional stress system. Now, as we are applying the force on the cuboidal body, there will be two things that will happen. One will be the change in shape and the other will be the change in dimension. Means the total strain is divided into two parts, that is change in shape and change in dimension. The change in shape, that is distortion, will be caused because of the shear stress, and change in dimension will cause because of the normal stress. Now consider the stresses responsible for the change in shape as sigma 1d, sigma 2d and sigma 3d. This indicates the distortion in three dimensions. And for the change in dimension, we can write sigma v. This v indicates the volume. If there is a change in dimension of the body, then there is change in the volume of the body. Now we can write the equation for the total strain energy as ut is equal to ud plus uv. Consider this as equation A, where ut is the total strain energy, ud is the distortion strain energy, and uv is the volumetric strain energy. From this, the applied stress in the direction 1 can be written as sigma 1 is equal to sigma 1v plus sigma 1d. Similarly, for sigma 2 and sigma 3, we can write as sigma 2 is equal to sigma 2v plus sigma 2d, and sigma 3 is equal to sigma 3v plus sigma 3d. If we add this sigma 1 plus sigma 2 plus sigma 3, we will get sigma 1 plus sigma 2 plus sigma 3 is equal to sigma 1v plus sigma 2v plus sigma 3v plus sigma 1d plus sigma 2d plus sigma 3d. Consider this as equation B. Since sigma 1d, sigma 2d and sigma 3d are the stress components which causes the distortion without any volume change, then it is clear that epsilon 1d plus epsilon 2d plus epsilon 3d is equal to 0. Consider this as equation C. There is no volume change which corresponds to the stresses which distorts the body. Now, as per the generalized Hooke's law, epsilon 1d is equal to 1 by E into sigma 1d minus mu times sigma 2d plus sigma 3d. Similarly, for epsilon 2d and epsilon 3d, we can write as epsilon 2d is equal to 1 by E into sigma 2d minus mu times sigma 3d plus sigma 1d, and epsilon 3d is equal to 1 by E into sigma 3d minus mu times sigma 1d plus sigma 2d. If we substitute these values in equation C, then we will get after simplification as sigma 1d plus sigma 2d plus sigma 3d into 1 minus 2 mu is equal to 0. From this equation, there are two possibilities to satisfy the equation. The first is either 1 minus 2 mu is equal to 0, or sigma 1d plus sigma 2d plus sigma 3d is equal to 0. Now if we consider 1 minus 2 mu is equal to 0, then we will get mu is equal to 0.5, which indicates the incompressible body, which is not possible practically. So we need to consider the second possibility, that is sigma 1d plus sigma 2d plus sigma 3d is equal to 0. Let us consider this as equation D. When we substitute this equation D into equation B, we will get sigma 1 plus sigma 2 plus sigma 3 is equal to sigma 1v plus sigma 2v plus sigma 3v plus sigma 1d plus sigma 2d plus sigma 3d. Further solving, we will get sigma 1 plus sigma 2 plus sigma 3 is equal to sigma 1v plus sigma 2v plus sigma 3v. As from the equation D, sigma 1d plus sigma 2d plus sigma 3d is equal to 0. Now, since the applied stresses are equal to only volumetric components, therefore we can take sigma 1v is equal to sigma 2v is equal to sigma 3v as sigma v. Therefore, the above equation becomes sigma 1 plus sigma 2 plus sigma 3 is equal to 3 sigma v. From this equation, sigma v becomes sigma v is equal to sigma 1 plus sigma 2 plus sigma 3 divided by 3. Consider this as equation E. We have the total strain energy equation as ut is equal to ud plus uv. Now let's find out this volumetric strain energy uv. The volumetric strain energy can be written as uv is equal to 1 by 2 sigma v epsilon v. So this epsilon v is the strain in x, y and z direction, or in first, second and third direction. So we can write for epsilon v as epsilon v is equal to epsilon 1 plus epsilon 2 plus epsilon 3. Again, as per the generalized Hooke's law, epsilon 1 is equal to 1 by E into sigma 1 minus mu times sigma 2 plus sigma 3. Similarly, for epsilon 2 and epsilon 3, we can write as epsilon 2 is equal to 1 by E into sigma 2 minus mu times sigma 3 plus sigma 1, and epsilon 3 is equal to 1 by E into sigma 3 minus mu times sigma 1 plus sigma 2. So if we substitute the values of epsilon 1, epsilon 2 and epsilon 3 in the equation of epsilon v, which is epsilon v is equal to epsilon 1 plus epsilon 2 plus epsilon 3, So we will get this equation. Now, if you take sigma 1 plus sigma 2 plus sigma 3 divided by E and sigma 1 plus sigma 2 plus sigma 3 divided by E as a common, then we can rewrite this equation as epsilon v is equal to sigma 1 plus sigma 2 plus sigma 3 divided by E into 1 minus 2 mu. Consider this as equation F. We have sigma v is equal to sigma 1 plus sigma 2 plus sigma 3 divided by 3 as equation E. Then the volumetric strain, that is UV is equal to 1 by 2 sigma V epsilon V, becomes, after substituting the values of epsilon V and sigma V, it becomes like this: UV is equal to 1 by 2 into sigma 1 plus sigma 2 plus sigma 3 divided by 3 into sigma 1 plus sigma 2 plus sigma 3 divided by E into 1 minus 2 mu. This gives UV is equal to 1 minus 2 mu divided by 6E into sigma 1 plus sigma 2 plus sigma 3 bracket square. Now we got the volumetric strain energy UV from the total strain energy equation UT is equal to UD plus UV. In the previous theory, that is in the total strain energy theory, we had derived the equation for UT as this. Now substitute the values of UT and UV in the above equation to calculate the distortion energy UD. First, rearranging the equation for UD as UD is equal to UT minus UV, and substitute the values, we will get this equation. After solving this, we will get UD is equal to 1 plus mu divided by 3E into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma d minus sigma 2 sigma 3 minus sigma 3 sigma 1. This is the distortion energy equation in three-dimensional case. This equation can also be written in another form by multiplying and dividing by 2 as this. We just multiply and divide it by 2. Now this 2 sigma 1 square can be written as sigma 1 square plus sigma 1 square. Then 2 sigma 2 square can be written as sigma 2 square plus sigma 2 square, and 2 sigma 3 square can be written as sigma 3 square plus sigma 3 square. So this sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2 is nothing but sigma 1 minus sigma 2 bracket square. Then sigma 2 square plus sigma 3 square minus 2 sigma 2 sigma 3 is nothing but sigma 2 minus sigma 3 bracket square, and sigma 3 square plus sigma 1 square minus 2 sigma 3 sigma 1 is nothing but sigma 3 minus sigma 1 bracket square. So this distortion energy equation can be written as UD is equal to 1 plus mu divided by 6E into sigma 1 minus sigma 2 bracket square plus sigma 2 minus sigma 3 bracket square plus sigma 3 minus sigma 1 bracket square. So the distortion energy can be written in both the form as this. We can use any one equation from this while solving the numerical. So this is the distortion energy in 3 dimension. Now, when the standard specimen subjected to a simple tension test, then the principal stress can be equal to yield stress, that is sigma 1 is equal to sigma yt, sigma 2 is equal to 0 and sigma 3 is equal to 0, as we are considering the simple tension test. When a component or a body is subjected to simple tension test and when the principal stress equals the yield stress, then the strain energy due to distortion becomes UD is equal to 1 plus mu divided by 3E into sigma square yt in simple tension test. This is distortion strain energy in simple tension test. For safe condition, the strain energy at distortion should be less than the strain energy in simple tension test. That is, UD should be less than UD simple tension test. So, if we put the values, we will get 1 plus mu divided by 3E into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1 less than 1 plus mu divided by 3E into sigma square yt. So from this equation, if we cancel 1 plus mu divided by 3 from both the side, we will get sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1 less than sigma square yt. This is the safe condition for three-dimensional case or triaxial case. For biaxial case, the safe condition like sigma 3 is equal to 0. So the above equation becomes sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 less than sigma square yt. So this is the safe condition for biaxial case, or we can rewrite this equation as under root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 less than sigma yt. And in terms of factor of safety, it can be written as sigma yt divided by factor of safety is equal to under root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. Now, considering the region of safety, the sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 less than sigma y square, if we rewrite this equation as sigma 1 divided by sigma y bracket square plus sigma 2 divided by sigma y bracket square minus sigma 1 divided by sigma y into sigma 2 divided by sigma y less than sigma y square divided by sigma y square, that means dividing by sigma y square on both the sides. Again, simplifying, we will get sigma 1 divided by sigma y bracket square plus sigma 2 divided by sigma y bracket square minus sigma 1 divided by sigma y into sigma 2 divided by sigma y less than equal to 1. This is nothing but the equation of ellipse. Therefore, the region of safety for the distortion energy theory is ellipse, and it can be plotted as this. If point coordinates for the biaxial stresses sigma 1 and sigma 2 lies inside this region, and if that coordinates are used to fix the dimensions of the component, then it is considered to be safe design. And if the coordinates of the point lies outside this region of safety, then component designed with these coordinates will fail. Then the pure shear case. For the case of pure shear, the principal stresses become sigma 1 is equal to tau and sigma 2 is equal to minus tau. Now, if you substitute the value of this sigma 1 and sigma 2 in the biaxial stress equation as under root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 less than sigma y, or sigma y is equal to under root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2, we will get the new equation as this. Simplifying, we will get sigma y is equal to under root of tau square plus tau square plus tau square, means sigma y is equal to under root of 3 tau square, or sigma y is equal to root 3 tau. That means tau is equal to sigma y divided by root 3, means tau is equal to 0.577 sigma y, or sigma 1 is equal to 0.577 sigma y. This relationship defines the shear yield strength sigma ys of any ductile material as a function of its yield strength in tension determined from the tensile test. Therefore, sigma ys is equal to 0.577 sigma y. The distortion theory is best suited for ductile material and cannot be applied on brittle material, since the limiting stress in elastic limit differs both in tension as well as in compression, and this theory cannot be applied on the component subjected to the three-dimensional compressive loads. But this theory gives the excellent and exact predictions for the ductile materials in biaxial loading cases. Now, let's solve one numerical according to this theory. The question is, the principal stress at a point in an elastic material are 200 megapascal tensile, 100 megapascal tensile and 50 megapascal compressive. If the stress at the elastic limit in simple tension is 200 megapascal, determine whether the failure of the material will occur or not according to von Mises theory. Take Poisson's ratio as 0.3. The given data is sigma 1 is equal to 200 megapascal, sigma 2 is 100 megapascal, and sigma 3 is minus 50 megapascal as it is compressive, and sigma y is equal to 200 megapascal. Poisson's ratio is 0.3. The safe condition according to von Mises theory is the distortion strain energy should be less than the strain energy in simple tension test, that is UD should be less than UD simple tension test. We know UD is equal to 1 plus mu divided by 3E into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. If you substitute the given values, then we will get this. After solving, we will get UD is equal to 1 plus mu divided by 3E into 47,500. Now consider this as equation 1. Now the distortion strain energy in simple tension test can be given as UD in simple tension test is equal to 1 plus mu divided by 3E sigma y square. This sigma y is given as 200 megapascal. Therefore, the UD in simple tension test is equal to 1 plus mu divided by 3E into 200 square, and which will get 1 plus mu divided by 3E into 40,000. Consider this as equation 2. Now comparing the equation 1 and equation 2, we will get 1 plus mu divided by 3E into 47,500 greater than 1 plus mu divided by 3E into 40,000. Now, which is the failure condition? Because UD is greater than UD in simple tension test, hence the failure will occur. This is all about the maximum shear strain energy theory or Henke-von Mises theory. Stay tuned with the Designgekz for more learning videos. Thank you.